It's a pleasure to introduce Dan Loughran from the University of Bath, who will talk to us about a quantitative version of the fibration method.
Thank you, Samir, and thank you very much to the organisers for giving me the opportunity to speak. So, yeah, the motivating question that I'm interested in this talk is the following. So, given a family of varieties over Q, how many have a rational point? So there's already been a few talks about this already in the conference. And yeah, the aim of this talk is to prove some results for completely general, well, for very general families of varieties. What I mean is, you know, there's been some talks about hypersurfaces and conics and things, which have been great, but I want to just, my varieties, I want them to be anything and just see how far I can go. Okay, so to make this question more precise, I'm going to introduce some notation for the setup. So let pi from V to projective n space be a dominant morphism with geometrically integral generic fiber. And V is smooth and projective. So, yeah, this one viewing is my family of varieties parameterized by the fibers of the morphism pi. And I want to count how many have a rational point. So I'm going to use the normal naive height on the projective space, the usual height, which, just to remind you, the height of a projective point with coordinates x0 up to xn is just a maximum of the absolute values of the coordinates, provided I chose a representative which was a primitive integer vector. So I need where's the what? Oh God, descente. No, this one. Yes. Monte array disjunction.
Green is up and the other one is down.
This array Monte disjunction.
But you can write in the black. Just write on it.
Okay, I see. Oh, this is a good one. Okay, this is the one I can write on. All right. Okay, yeah. So I introduce the counting functions. Yeah. So this one is counting the number of varieties in the family with a rational point. So yeah, points x in projective space, height less than or equal to x, such that the fiber has a rational point. Yeah, so Vx is the fiber over the point x. Oops. And I'll also be interested in the closely related counting function, which counts those of bounded height for which the variety is everywhere locally soluble. So it has an adelic point. And I can state right away first thing I want to talk about, so this is a film Ephemios mentioned already, but a recorded statement proved by myself and Arne Schmitz a few years ago. Yeah, so an exact generality I've stated there. We get an upper bound for the number of varieties in the family with a rational point. It's b to the n plus 1 over log b to delta pi for some factor delta pi, which could be 0. Yeah, and I should say, I mean, how we actually prove this result, I mean, we get an upper bound for those ones which have a rational point, but to do this, we get an upper bound for the ones which are everywhere locally soluble. So, I mean, the actual theorem is this, but of course, everyone's interested in rational points. But then, if you're not everywhere locally soluble, then you certainly don't have a rational point. So, the theorem is really, yeah, what we actually prove is an upper bound for those everywhere locally soluble. And I'll define this invariant delta because theorems won't make sense otherwise if you don't know what on earth it is. So this is the definition of delta, so I'm going to have to let d and Pn. So this is a point of codimension 1, so it's you can think of this being the generic point of a divisor, irreducible divisor in projective space. Go on then and choose a finite group. Gamma of d through which the absolute Galois group of the residue field of d, which this group acts on the geometric irreducible components of the fiber above this point. Yeah, so I was saying, so getting a point, codimension 1 point, it's the generic point from divisor. I look at the fiber over this point. In general, this will not be irreducible. It'll break into some irreducible components. And I'm interested in the irreducible components of the algebraic closure. So this is what I'm calling geometric irreducible components. But the absolute Galois group of the function field of D permutes these, moves them around in some way, and it acts via some some finite group. I mean, choose a splitting field of all these irreducible components. So that's all this finite group is. So then I define a local invariant little delta of capital D of pi. That's a number of elements gamma in the Galois group such that it fixes a geometric irreducible component of multiplicity 1. Yeah, so the components of multiplicity 1, there's just those which are generically reduced. And then you need to renormalize to make sure this is well defined independently of the choice of gamma, which divided through by the total number of elements of the group. And then this invariant capital delta, you take the sum over all codimension 1 points, and then you take 1 minus the little deltas. Let's send this one. Cool. Now some remarks. First one is, yeah, this sum is really finite. Only finitely many codimension points matter. And in fact, the ones you only care about where there's non-split fibers. So yeah, so I'll say only non-split fibers contribute to, well, can contribute non-trivially to this sum being there. Everything else is just going to give you a 0 if you're split. And I will call for you, so yeah, so say that a fiber over one of these points is split if it contains an irreducible component of multiplicity 1, which happens to be geometrically irreducible. Yeah, so you only care about these non-split fibers. And yeah, a big motivation for me and Anglais when we were proving this was a result of Serre from the 1990s. So it's theorem 0 generalized. The case of families of conics. Which was treated by Serre in this level of generality in 1990. Yeah, so Fimios mentioned this already in his talk, so Serre got quite general results here. And then here, for case of conics, this invariant delta is quite easy to calculate. You know, you think, okay, there's lots of data. Technically, it's just finitely many data. You have to calculate this finite groups at finitely many points, and all this how they're acting. But for families of conics, there's a simple formula. It's just a half times the number of codimensional points on the projective space, such that the fiber over this point is non-split. And yeah, non-split for conics is quite easy. So it has to be singular, and it turns out you can't get a double line. You have to get two lines meeting in a point. And non-split just means the Galois group is these two lines are not defined over the ground floor, they're defined over a quadratic extension, and they'll be switched by some Galois action. So yeah, it's quite easy to see. Here, I mean, yeah, so the group, this gamma D in this case has order 2, and the trivial element is counted, but the non-trivial element is not counted, so this gives you the half, and then you've got 1 minus a half is a half. So that's why you get a half here. Cool. And then both Serre and us asked whether the bounds we obtained are sharp. And it's been shown in some cases, like special cases, special families of conics and Brauer-Manin varieties and things. But what I've done with my co-author Lilian Matthiesen is we can show it sharp for some quite generality. Anyway, that's what I'm going to write down now. Theorem. Tableau 1 goes up, and then I want oh god, how do I get that one down? Ah, there's no, okay, there's nothing written there, that's why. It's not just me, there's nothing written there. Okay, good. Okay, cool. So this is the first film I'm going to talk about, film 1, due to myself and Lilian Matthiesen. So it was on the archive a couple of weeks ago. Yeah, so I won't recall the whole assumptions. It's an exact generality, as in theorem 0, but we're only looking at the case of pencils, such as fibrations over the projective line. But yeah, so V smooth projective, generic fibers, geometrically integral. And I'll write down assumptions. So assume that first assumption just says make sure you don't count the empty set. So you're assuming there exists some Y in projective line such that the fiber over this point is smooth and everywhere locally soluble. Yeah, I should say, so if you want the bound in the theorem, okay, it's disappeared. Yeah, if you want the bound to be sharp, then not only do you need to have a fiber which is everywhere locally soluble, but you also need to have a smooth fiber which is everywhere locally soluble, because the singular fibers, I mean, it's just going to be a finite set of them. Next condition says that for all, so we're working over the projective line. So codimension one point is just a point. I mean, it's a closed point on P1. We want fiber over this point. It needs to have an irreducible component by multiplicity 1. Yeah, so we're not asking this irreducible component is geometrically irreducible, because then that'd be really easy, make everything really easy. And this condition 2, I should say, turns out to be necessary for the upper bound to be sharp, because if you have lots of, I mean, there's this paper due to Colitilen, Swinton Dye and Alexis Golbogotov, where they look at this kind of case. If you've got many double fibers, then you expect very few rational points in general. And also, we showed also there's very few fibers which are everywhere locally soluble. So this one, 2 is also necessary. Cool, and then the important assumption is that all non-split fibers of pi lie over rational points. Great, then if we count the number of varieties in the family which are everywhere locally soluble, which are upper bound is sharp in this case, so it was b squared to log b to the power of delta pi. So the upper bound is the correct one. And yeah, a cool thing about this theorem is, yeah, we don't assume anything about the varieties in the family. I mean, you know, the curved surfaces, general type finite, it doesn't matter. But we're only counting those which are everywhere locally soluble. Yeah. So I'm just going to go straight to the proof. So what we do, yeah, I mean, we're going to construct functions which detect when a fiber is everywhere locally soluble. And to do this, I need to set up some notation. Yeah, so I'm going to choose some large finite set of places S, and I'm going to allow myself to increase this as required for the proof to make sure everything works. And I'm also going to choose a model for my morphism over Z. So just to make sure I can talk about reduction modulo P, I'll be lazy, I won't bother. Just to stop the notation getting a mess, I'm not going to use a new notation for it, but I just want to say reduction modulo P is going to be well defined, at least away from, well, it's going to be well defined. Pardon? No, nothing's happened yet. Yeah, that doesn't do anything yet. What I'm saying is, choose a large enough set of places S at the beginning to make sure what's going to follow works. Yeah, probably I should choose a set S after I chose my model, but anyway. Cool, and I'm going to let L1 of x0, x1, dot, 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 up to LR of x0, x1. So these are going to be primitive binary linear forms such that yeah, so my assumption 3 was all the non-split fibers lie over rational points. So these are going to be the ones which give you the locus, the non-split locus. So this is going to be, I call this DI. It's a rational point in P1. Yeah, such that the points lie below all the non-split fibers. And then I'm going to choose a finite group as in the definition of these delta invariants. So choose a finite group, gamma I. Yeah, so same as exactly same in the delta invariants through which the absolute Gauss group. So now, I mean, the residue field of my point is Q, so it's really just the absolute Gauss group of Q. This acts on the geometric irreducible components of the fiber over the point DI. And then I'm also going to construct a set of primes, P, which is, I throw all the bad primes in my set S into there, but then the important primes are those primes not in S, such that the Frobenius element at this prime, when I view it as m gamma I, yeah, I should say, so increasing my set of places S, I can make sure P isn't ramified in the Galois extension corresponding to gamma I. So the Frobenius element of prime fixes a geometric irreducible component of multiplicity 1. Cool, then I'm going to define some completely multiplicative functions. So it's omega I from the natural numbers to 0, 1. So these are going to be indicator functions. And it says if you input a prime, yes, it's completely multiplicative, so it's just determined by its values on primes. So if you put a prime in, you're going to give 1 if the prime lies in the set of primes Pi associated to the ith non-split fiber, and it's going to be 0 otherwise. So it's indicator function for those prime it's indicator function for those natural numbers whose prime divisors must lie in the given set Pi. So now that's just a notation. Now I can tell you how I use these indicator functions to detect local solubility at least the large primes. So the lemma here is as follows. So yeah, I'm after large S. So larging S if necessary, the following holds. So I'm going to let x0, x1 in z squared. It's going to be a primitive integer vector. then if, so I take the product from I equals 1 to R of my indicator functions omega I, and I evaluate them at the ith linear form. So if this is equal to 1, then the fiber over my point x has a periodic point, and this is for all p not in S. Yeah, so these explicit multiplicative functions which allow you to detect local solubility at the large primes. And I'll prove the result, because... Oh, yeah, so yeah. So I'm just saying, yeah, these functions, they allow you to detect local solubility of the large primes. Yeah. And I'll prove it for you. So proof of the lemma. Yeah, so first thing is under the assumptions which are there. God, it's high up, isn't it? Okay, yeah. So we claim that under these assumptions, if I look at the fiber over x modulo p, this is split in the sense I defined earlier. So it has a irreducible component to multiplicity 1, which is geometrically irreducible. So I'll prove this claim for you. Oh yeah, sorry, yeah, so it's split. I mean, yeah, P is not in S. Yeah. Okay, so first case is when essentially nothing happens. So I'm going to first suppose that my prime doesn't divide the product of these linear polynomials. What does this mean geometrically? Well, these linear polynomials were telling you the zero locus of the non-split fibers. This means, i.e., that P is not congruent to one of the di modulo P. So x. Yeah. So modulo P, x doesn't lie below one of the non-split fibers. And by a kind of spreading out argument, you know, so these di tell you where the non-split fibers are over Q. And providing you choose your prime sufficiently large, which I'm free to do, they also tell you where the non-split fibers could lie modulo P. So I'm away from the non-split locus. Yeah, so here away from the non-split locus, providing I a large S. So the fiber is non-split, it's split, yeah. Next case. Now assume that P divides L1, well, ally of x0, x1. This means that my point x is congruent to di modulo P. So here, I do coincide with a non-split fiber modulo P, so I could possibly be non-split. However, I've set up everything correctly so this doesn't happen. Namely, yeah, but now I calculate omega I evaluated at Li. So by assumption, this was equal to 1. So this in particular applies, this is completely multiplicative, and P divides Li. This means omega I of P is equal to 1. So that is equal to 1. And just the definition of these completely multiplicative functions means that P lies in the set Pi. Great. But then, since P is in Pi, this is exactly defined to be those elements such that the Frobenius element fixes an irreducible, geometric irreducible component of multiplicity 1. Above the fiber over di modulo P. well, I say above, I mean, yeah, of this fiber modulo P. And it's because, I'm working over a finite field. So the Galois action is completely determined by how the Frobenius element acts. And the Frobenius element fixes an irreducible component multiplicity 1. So the whole Galois group modulo P must fix an irreducible component of multiplicity 1, which means there's an irreducible component of multiplicity 1 which is invariant into the Galois action, so it must be geometrically irreducible. Hope that makes sense. So if I'm looking at the fiber over my point x, which I'm interested in, so modulo P, it's just congruent to the fiber over this guy. So this is split. So that proved the claim. And now I can complete the proof of the lemma. So I need to show there's a I'm going to show there's a QP point. To do this, so I use, by the Langue estimates, we find that this fiber modulo P, since it's split, it's got loads of points. In particular, it has a smooth point. Smooth FP point. And here, in order to do this, I have to possibly increase my set of places S. But the amazing thing about the Langue estimates is they're completely uniform in your choice of point. So I can increase this uniformly, independently of X. So this is, again, enlarging S if I need to. And then, since it's got a smooth FP point, I just apply Hensel's lemma to deduce there's actually a QP point. No, I want to one. Yeah, so I've used these completely multiplicative functions, omega I, to detect local solubility at the large primes. Now I need to take care of the small primes, but that's easy, and this is the point. I use the fact that there's some fiber which is everywhere locally soluble. So how do you get local solubility at the small primes? Yeah, so I say, recall there was we assumed there was some point such that the fiber is smooth and everywhere locally soluble. So then all we do is we just approximate, at any prime we can approximate this fiber. So if if x is close to y in the p-adic topology, then since the fiber over here has a smooth QP point, you get one in by fibers by the p-adic implicit function theorem. And this also implies, I'm allowing p equals infinity here by p-adic implicit function theorem. So at any given finite list of primes, we can always guarantee local solubility, providing we approximate. So what's the conclusion? So we want to count the number of fibers which are everywhere locally soluble. It's greater than or equal to, so I have a half, just because I'm going to move from a projective counting problem to an affine one. So I'm counting x0, x1 in z squared, primitive, bounded height. And then I need to approximate my given fiber. So I'll say, so there exists delta greater than 0, such that providing I'm in the distance delta, so maybe you're worried about division by 0. Well, I could just move my fiber to begin with. I can make sure y0 is not 0. And this is for all small primes and place. Yeah, so implicitly I'm assuming S contains the infinite place. And then what do I have to sum? I have to sum the product of my indicator functions. Omega I evaluate a linear form. Great, yeah, so this is less than equal to. Cool. And we want a lower bound. So we've rewritten the counting problem now in terms of, yeah. So this is a sum of multiplicative functions evaluated at linear forms. And there is big business around studying things like this. So there's fundamental breakthroughs by Green and Tao, I guess joint also with Ziegler. Ziegler, using techniques from additive combinatorics, and Lilian Matthiesen has also done a lot of work on problems of this type. Yeah, so there's quite a bit of work on sums of multiplicative functions evaluated at linear forms. You can get asymptotic formulae for these kind of problems. I'll say a little bit about these conditions. Okay, yeah, these two are obviously fine. Okay, we have a coprimality condition. Well, you can deal with that using Mobius inversion. One problem with these methods is they don't give you uniform error terms. But yeah, the contribution from those whose greatest common divisor is large is negligible. So you can assume the greatest common divisor is very small. So it doesn't mess with uniformity in error terms. These conditions here, so yes, if a p equals infinity, it's more or less like just a union of cones in R2. So it's a very mild linear conditions being imposed in the infinite place. And for p is not equal to infinity, this condition here you can rewrite. You can basically rewrite it just in terms of congruence conditions. So ultimately, we reduce to some counting problem with some counting points in a region with some congruence conditions imposed. And we apply the additive combinatorics machinery. And I'm not going to do that on the board. I mean, Lilian's the expert. And she's giving me a talk in a few weeks, I guess. Maybe, I don't know what she's talking about. Yeah, so by the power of additive combinatorics, you find that this quantity up here, these sum of multiplicative functions, so we get an asymptotic formula for the sum. But anyway, it's bounded up by, so you get b to the n plus 1, and then you get log b, and it's so I need product here. So product I equals 1 to r. Oh, thank you. Yeah. Thanks, I'm in P1. Yeah. And then you need to have it's the order of the singularity of the corresponding Dirichlet series, which since mine's just indicator function for sets of primes, well, you just have to take the density of the set of primes I was allowing, and then minus 1. But, yeah, maybe you forgot what the set pi was. But anyway, you can quite easily check that I've set everything up correctly, so the set of primes. So this was exactly those whose Frobenius element fixed in the irreducible component of multiplicity 1. And that's just the density of the set of primes is exactly the same. So this was counting all elements which fix an irreducible component of multiplicity 1. The renormalized counting those elements of the Galois group which fix an irreducible component of multiplicity 1. And these two are equal just by a simple application of the Cherenkov density theorem. Great, yeah, so that's a sketch of a proof of theorem 1. And I've still got some time. Yeah, so probably you're thinking, this is a conference about rational points. You know, well, who cares about everywhere local solubility? Well, I do, but also, I also care about rational points. So, obviously, the biggest problem in general is you need to control failures of the Hasse principle, and we were able to do this in some cases. So this is theorem 2. Due to myself and Lilian Matthiesen. Yeah, so we're still looking at vibrations of a P1. So pi goes from V to P1. Yeah, be a dominant morphism. With, so my usual assumptions, I mean, yeah, with V, smooth projective. And I'm going to write down the assumptions. So first of all, we need to make sure we're not counting the empty set. So assuming there's a rational point. Part 2, so we're going to assume something about the Brauer-Manin obstruction being the only one for the fibers. And it's not in many cases. So I'm just going to assume that the generic fiber is rationally connected. And we have general results, but you need some cohomological conditions on the generic fiber. Third condition is the one which you need to get the additive combinatorics machinery to work, which is each non-split fiber lies over a rational point. And we, no, not that one, this one. Yeah, we want to have some control over the Hasse principle, so we need to assume that the Brauer-Manin obstruction is the only one. So the Brauer-Manin obstruction is the only one to the Hasse principle. For the fibers of pi. Great. Cool, then I can write the conclusion. Then it says there exists some factor omega pi greater than or equal to 0, such that if you count the number of varieties in the family with a rational point, this is bounded by the b squared over log b to omega. Yeah. So I should give some remarks. Yeah, first of all, when you say what is omega, well, when I show you the proof, you'll see what value we get. So proof gives explicit value for omega. I don't know whether the value we've got is the correct one, basically because there's so little known corresponding upper bounds in this area. But hey, we got some value. I mean, Thimios said it's even difficult to get a small power here, bt epsilon, so we got something which is very close, just within a power of a logarithm for what the correct answer should be. I mean, I don't know what it should be in general because you don't know how to control the Hasse principle in general. Yeah, second remark is, yeah, I should mention work of Harpaz and Wittenberg. So they showed that. So in this setting, though, dropping condition 1 because they were interested to know when do you even have a rational point. So they showed the Brauer-Manin obstruction for such varieties was the only one. So if the Brauer set is non-empty, this implies there is a rational point. So yeah, so condition 1, knowing this is a rational point. This known in Brauer-Manin obstruction is the only one in this case. And how they prove this? Yeah, so they prove this by constructing a fiber with no Brauer-Manin obstruction. Well, constructing an ever locally soluble fiber with no Brauer-Manin obstruction. So in particular, since we're assuming the Brauer-Manin obstruction is only one to the Hasse principle, that allows them to deduce the existence of a rational point in this case. And basically, yeah, I mean, the method of proof is inspired by their proof. Yes, our proof is what can be viewed as a quantitative version. Quantitative version of the method. So this is the quantitative version of the fibration method alluded to in the title. Are there any questions before I start the proof? Okay. So we need to control the Brauer-Manin obstruction. Great. So I'm going to let A be a finite set of representatives of the elements of the generic Brauer group. So it's a Brauer group. So eta is the generic point, the Brauer group of the generic fiber modulo the constant ones. Yeah, maybe I didn't say, I'm working over Q. Oh yeah, okay, there's a Q there. The results all over Q. Yeah, so look at the Brauer group of the generic fiber, and I quoted out by the constant algebra for the generic fiber. Our conditions that the generic fiber is rationally connected implies this group is finite, and we choose some representatives for it. And these representatives, you can spread them out to elements of V, the fiber of V over U, where U in P1 is some dense open. Yes, this is just the inverse image of U I'm writing here. Yeah, so this set alpha is the generic Brauer group elements. And one of the great things is the generic Brauer group elements, in fact, almost always generate the Brauer group elements of the fibers. So I think this observation due to Harari originally. Harari. So some thesis. Yeah, there is a thin set omega in P1 Q such that for points not in this thin set, so maybe I'll be able to say, yeah, so those points, I want to make sure I'm lying in U at least where they're defined, but which don't lie in my thin set. Yeah, the map given by taking a generic Brauer group element and you can restrict it, so it's well defined since I'm working on my set U. I restricted just the fiber here, modulo constants. So this map is an isomorphism. So the generic Brauer group generates the Brauer group of almost all of the fibers, where almost all is in a quantitative sense. Yeah, so if you want to count, since I'm in projective line, the number of points are bounded height in any given thin set. It's bounded above by b to 3 over 2 plus epsilon. So I went on counting. The points where this condition fails is negligible for my count. So I can always assume in my counting problem that the Brauer group of the fiber is generated by the generic Brauer group. Yeah, so I can assume that my choice of representatives generate Brauer group of the fiber modulo constants. Cool, and then to each element in the Brauer group, you can associate Brauer survey scheme. So say that again, please. Yeah, definitely, yeah. I mean, yeah. I'm using this the rationally connected assumption all the way throughout the proof. Yeah. Okay. Well, it is an important point. Yeah. Yeah, I can associate Brauer survey scheme. So it's like, you know, if you've got a quaternion algebra of a field, you can associate a conic to this, and this instruction you can do completely in families. And you've got some Brauer group, you can associate some Brauer survey scheme over I'll call this y alpha to VU, and I'll call the map psi alpha. And what properties does this have? This is such that for all fields K and all points P, I'm using X. Hang about. So P is in for U of K, so we have that when I evaluate my Brauer group element at P, I get 0. This is in the Brauer group of the field K, if and only if the fiber over this point P has a rational point. So I'm going to use these Brauer survey schemes to detect whether my Brauer group elements are evaluating trivially or not. Cool, now I've got these Brauer group elements in these Brauer survey schemes alpha, and I just throw them all together. So I choose a smooth compactification. I put up psi from Y to V of just the fiber product of the Y alphas, because I'm going to simultaneously want all these Brauer group elements to vanish. So I can do that by taking their fiber product and evaluating it there. Okay. Now it's a little bit more setup. Yeah, so recall that I have some point P, rational point. So under my assumptions, so yeah, Harpaz and Wittenberg, not only did they show Brauer-Manin instructions only want Hasse principle, they also showed it's only one to weak approximation. In particular, the rational point is risky dense, so I can choose my point, which lies in VU, so that my Brauer group elements are well defined and things there. Anyway, I can choose. I've got a lot of flexibility by choosing it, and I'm going to evaluate my Brauer group elements there. But I can change my choice alpha by a constant algebra. I'm changing each of them of the Brauer group of Q, which is not going to change any of the setup at all.
But maybe you should mention that this interpretation of Harpaz and Wittenberg method is due to quantitative. It's very broad.
Okay. Thank you, colleague. Then. No, I think I remember reading this interpretation. You have these nice notes in Arizona Winter School. I think I remember reading that. Yeah, changing alpha by element blah. Yeah. So we have that. So if I evaluate alpha, my chosen point P, which I've fixed, in general, this is some element to the Brauer group of Q, but I can just make it be 0 by just changing my initial choice of representatives for alpha and my choice of representatives. And then if you think a moment what this means that not only does V have a rational point, but Y has a rational point. The image product of Brauer-Survey schemes has a rational point because this is set up exactly to have a rational point if and only if there's something which evaluated. Yeah, I mean, did you get 0 here? I mean, I wrote it there. Anyway, yeah, this fact here. OK, now I can try and do the proof. So I tell you what we want to do, how we want to prove the theorem. So we want to apply theorem 1 to this composition. So this is my original fibration. This is these Brauer-Survey schemes. OK, so then this gives now the lower bound. So the number of fibers for the composition, which are everywhere locally soluble, is greater than b squared over log b to the delta of pi up psi. And I should say now, this is what this is the exponent which we actually get in the theorem. Well, yeah, this is an immiscible exponent we get in here. So it's just the delta invariant, not v, but of some other morphism closely related to delta v. OK, then the key lemma is that I was originally interested in the number of fibers. Obviously, yeah, this is pi psi. So the number of fibers of pi which had a rational point, and I claim this is greater than or equal to the thing I just did. So the number of fibers of the composition which are everywhere locally soluble. And how do you see this? This is the key trick somehow, because yeah, so for x counted by n log pi psi b, yeah, for all places v, there exists a point qv in the fiber. And this is all just a definition of this counting function. So now let pv be the image of this point. Oops. Now in the fiber of v above x. Then for all alpha, so I'm interested in the Brauer-Manin obstruction. So I take one claiming is this adelic. I've just constructed an adelic point, so I'm claiming it's orthogonal to the Brauer group. So I look at the sum of the local invariants of alpha evaluated at PV. But I've arranged set everything up so that there's a rational, well, there's a QV point above this fiber. So it means that when I evaluate it, I just get 0 here, because this is how these Brauer-Survey schemes were designed. So this is just a sum. I'm just summing 0 all the time. So I'm just getting 0. That's great. That means that the Brauer set of the fiber is now empty. Not empty. Yeah, this. There's no Brauer-Manin obstruction for such a fiber. And I assumed Brauer-Manin obstruction was the only one. So I get a rational point in the fiber, which is what I wanted to show. And I'll briefly say a little bit more. So as I was saying, this is the proof we wanted to do. But we don't do this proof because there's a serious problem, is that this composition might not satisfy the hypotheses of theorem 1. And the important hypothesis is that the non-split fibers lie at rational points. So there could be, when I construct this morphism, I could have created more non-split fibers. So there could be non-split fibers now over non-rational points. And so the theorem 1 won't apply there. But there's a trick due to Harari from his PhD thesis for dealing with this kind of problem. And Harpaz and Wittenberg also use this trick. So what we actually do, we don't do this. We have to just go through the whole proof of theorem 1 again, apply in this case to the composition of these morphisms. And for these new non-split fibers, we have to pay careful attention to them. And say we don't arrange that all the local variants are actually equal to 0. There could be some which are non-zero, but there's this trick of Harari which allows you to choose a prime, like a fudge prime, which allows you to take any value of the local invariant. So you can arrange the sum of local invariants to actually be 0. And I think I should stop there. Thank you.
Questions, please?
Hey Dan, do you try to do it with morphisms to higher dimensional projective space?
Yeah, so the theorem 1 for everywhere local solubility, we can do this in some cases, like if you have a Brauer-Severi scheme over Pn, which corresponds to an algebraic Brauer group element, and we need some linear conditions, so it's only ramified along hyperplanes. We could do it in this case. The problem with doing it for arbitrary families of varieties over higher dimensional projective spaces, the first thing is there could be some codimension 2 behavior in general, which these methods don't see, because you just have a multiplicative function evaluated linear form. So all it sees is codimension 1. And you have codimension 2 behavior. So here you need to use Siver-Vekadal in general, and we didn't combine all the methods because it would just get a complete mess. But there's also another thing is, over higher dimensional bases, the splitting fields, irreducible components, are going to be taking place over finitely generated extensions of Q. Whereas these completed multiplicative functions, all they can see is number fields. So they can't deal with finite generated extensions of Q. So there's a couple of obstructions. Yeah, I mean, I said obstruction. Anyway, serious difficulties with doing it. And we could do this in some cases, because like this Brauer-Severi case, only codimension 1 is relevant because this is a Grothendieck purity theorem. Anyway, stuff like that, yeah.
More questions?
So in theorem 1, can you say anything about the leading constants in some cases?
Oh, yeah, no. The one thing is our way for constructing everywhere locally soluble fibers, all it knows more or less is information modulo P. So if you're saying to get everywhere locally soluble, if you're split modulo P, then we can get a p-adic point. But to really get some asymptotic formula and things, you need to take into account higher powers of P. I mean, it's a similar phenomenon in Phimios's talk. I'm not sure about, I've got some vague ideas, but in general, no, I don't know.
Any more questions? Okay, before we thank Dan again, I'd like to remind you that it's a conference photograph now, and we come back at 4 o'clock. Okay, let's thank Dan again.